Yeah, thank you, Mike. Thank you for the introduction. Okay, welcome everybody. Good to see you. Today I'm going to talk about multimodal video models for robot learning. To be a bit more specific, I want to talk about the fact that computer vision models, particularly video models, have a great potential for their usage in robot learning. It will be a bit different from video generation model Sherry talked about in the previous talk. This will be more about, vision language model, video-based vision language model you might be more familiar with. Okay, so first of all, I'll talk about some of my research on understanding long videos using VLMs. And then I'll talk about how all these, VLMs, multimodal models have been used for robot learning. And then I'll kind of give you a kind of suggestion, show you the potential that multimodal video models can actually serve as a zero-shot robot action policies. Okay, first about how to use video models for longer videos. I will not go into too much details, but we have studied several aspects. One aspect was to kind of attempt to capture motion information in videos in the form of the natural language, so that the VLMs and LLMs can actually take advantage of them. For example, if we are able to kind of track semantic objects such as hands, like bottle, cooking pan, lemon, and so on, and then represent their motion as a track, trace, or trajectory, whichever you want to call it. And then provide such information to the VLM, then VLM should be able to better understand what is going on in these videos. Since usually if you do kind of one frame caption, they miss the motion information. So this can be one way to augment the VLM. To be more specific, what we did was extremely simple. Given a set of questions and the input, we did some frame selection, we detected the objects, we did some matching to establish the correspondence between the object, essentially doing the tracking, and then just dumped all these information into the VLM, and then the VLM made a decision. So to be more specific, these are like the kind of, some examples of how the kind of visual traces of the objects we were able to obtain by taking advantage of simply off-the-shelf object detector and tracker, and then by giving this to the VLM to make the better decision on what is happening in the scene, for example, the VLM was able to make a better decision. Yeah, it was able to build on top of any existing baseline, and then was able to improve the accuracy by adding the motion information that way. Another aspect we kind of briefly touched was the frame selection. There are so many frames in long videos in particular, and we kind of explore the potential by learning to select frames intelligently based on their embeddings. We actually are able to provide a very small number of frames, like sometimes 32, sometimes even like 12 frames for the entire like 40-minute video, for example, and actually do a pretty nice, reasonable video question answering that way. So compared to previous work, yeah, x-axis is the number of frames or number of captions, and we still show that it is capable of doing good video question answering that way. Some more qualitative numbers, but again, I'll not go into too much details. We also studied like an alternative approach, which is not about selecting frames, but actually giving almost all the information in all the frames and forming a big repository, and then doing some iterative update within the repository, such as like writing to the repository, reading from the repository, similar to like the concept of working memory in human brain. And these concepts have actually shown the potential in us representing the information as text in videos, and then taking advantage of it for the actual longer video understanding. So all these things were interesting, and there was not only these works, but also other people's work, which made like progress in the field. However, today, the real topic I want to talk about is how can all these models actually benefit robot learning? And before going into too much details, I actually want to kind of mention that, yeah, for some people, particularly some computer vision people, are slightly scared of going into the robotics domain, but it's not really as kind of challenging as it seems. if we look at the typical formulation of supervised regression in computer vision, for example, classification, we have an input video and we have some function we are learning, and we are doing nothing but mapping it to some, one hot vector. I mean, back in the traditional computer vision days for classification. Now with VLM days, we are mapping such input into the text. More specifically, a sequence of language tokens by learning this function as well. In robotics, it's not really that much different. We can still keep the same supervised learning formulation. We can still learn the same function, same black box function, which can be lots of transformer layers. We can still learn to optimize such parameters. It is only that the output is now some control vector that is capable of controlling the robot manipulator or robot mobility or anything. So people have worked on lots of things, and let me give you some examples how computer vision VLMs have been directly benefiting such robot learning. This was one attempt, and as you can see, this was a VLM. This was a transformation of a pre-trained VLM into a vision language action model. They call it VLA. The input to VLM or VLA is something that you already will be familiar with. It will be text and the image, essentially what the robot is observing right now. And the output here, instead of generating some immediate control vector that can directly control low-level motors, we actually try to generate a bit more semantically understandable outputs as an action the robot can perform. Such as, the robot has to pick up the carrot, which is at this particular coordinate in image, and then rotate it by a certain degree, and then do something, and so on. So what we tried to do was to tune a pre-trained VLM into a powerful VLA model by describing actions purely in terms of text format, and then also fine-tune such VLA by incorporating the concept of visual instruction tuning, very popular in computer vision, in self-supervised auxiliary training data way. And this data curation enables faster representation transfer, and that's what we have been observing. I'm just repeating myself in some sense because you already probably will be all familiar with all these. The only difference between what you already are familiar with and this is that, now this is about controlling the robot, nothing more, nothing less. So in one of my previous work, RT2 at Google, we were able to design an approach that takes, vision with vision encoder, text with text tokenizer, and then feed it to the LLM, and then generate some specialized tokens as an output to control the robot. We modified it to something called Lara, which is an extension of Lava, describing everything in terms of the language output. And then on top of this, we added like visual instruction tuning data, which is actually particularly useful for the training derived from the video data we have. It can be as simple. I mean, these are like the actual training data. So these are training data which was originally for generating actions, but we kind of hacked it by saying that okay, object detection actually should be an important data if we actually want to manipulate the robot. I mean, manipulate the objects in the scene. Predicting how things will be moving in the future should actually be very relevant to robot understanding the scene so that it can actually do the action. So motivated by this, essentially we boosted the amount of data in self-supervised fashion, as mentioned, as simple as just locating the object, asking the robot to locate the object in this data. Or it can be a bit more complicated by saying that, okay, we have a video, essentially like a very simple form of a video, like 2 frames, and then asking the robot, okay, what action should have caused such scene change? And the robot should be able to answer that. And we can actually curate this kind of data almost automatically without any human annotation because we know what action was performed in our training data. Similarly, we can actually try to ask how the objects will be moving given the action, which is about the future prediction. So by simply feeding these types of data, we were able to learn much more quickly by just fine-tuning VLM in this fashion. By providing additional data, it was learning much faster. Here, x-axis is the amount of training data. And as you can see, compared to like previous RT2 style designs, we learn like 10 times faster. I mean, this is log scale, while actually obtaining better accuracy that way. So some of the things it was able to do, it was able to handle unseen tasks of like finding some specific objects it has never seen in the training data. Since this was pre-trained, we were building on the pre-trained VLM. It had a capability. It was able to inherit the capability that of recognizing objects. And then even if we kind of provided the unseen task of picking up some banana, which was never really in the scene, it was able to actually do the control. We showed better zero-shot accuracy compared to other approaches, even the big models. After fine-tuning, particularly with this auxiliary data, which is the data curation data I just talked about, it actually was able to essentially address the task. As mentioned, it was able to kind of resolve many unseen tasks, such as, if you want to give the dog the sweet food, I mean, which is really the unseen task, the robot was able to know that, okay, I should first pick up the dog and then put it next to the ice cream, for example. We also conducted experiments in more 3D-like environment where the command was more about, okay, it is time for you to pick up the cooking pot, which was never in the training data, but obviously it was in the VLM training data in the pre-training stage. So although the robot has never seen this robot action tasks, it was able to perform reasonable tasks. I mean, reasonable kind of, tasks with reasonable success accuracy. Okay, that was kind of one kind of example of how like VLMs have been directly benefiting robot learning. Another kind of question you will naturally kind of ask is, okay, is VLM the only vision model we can use for robot learning? Obviously, the answer is no, because diffusion is also very popular in computer vision. Okay, how can we benefit from diffusion model to solve the robot problem? As Sherry has presented in the previous presentation, one way is to generate the video. However, we took a different approach of using the diffusion model or hacking the diffusion model so that it actually generates something similar to optical flow. We hacked the diffusion model, image diffusion model, so it generates how the pixel will be moving in order to accomplish the task. And we gave such information to what we call system one, which is responsible for mapping such motion, pixel-based motion, into the actual robot control action. Omitting the details, if I actually show you what actually happened, we trained the diffusion model, which is able to generate the pixel movement. And then we gave such, and obviously this kind of training is very agnostic to embodiment. Given lots of robotics data, we train the model so that it is able to always predict how the pixel will be moving in the future. So this is not about optical flow computation. This is about the forecasting of the pixel motion. And once we have something like that, we gave that into the robot control. And this was more like a lightweight VIT, the transformer model you might be familiar with, similar to RT1. And then it was able to actually generate lots of like control vector corresponding to like pixel motion, which is much more coarse than the actual control. And that's the reason why we are calling it system one, system two. System two is a slow thinking. System one is faster thinking, but system two is a higher level thinking. So in system two, we provided like the frame rate at the 0.5 frame per second, and it was generating. What you are actually seeing is the actual example of the motion, pixel motion it is generating. The color indicates the orientation, and it is able to show which pixel has to move into which direction, visualized with arrows here as well. And by taking that as an input, as well as some of the raw frames at a higher frequency, the system one was actually able to move the actual gripper manipulator into the desired location. So more examples moving in 3D based by computing the pixel motion for some of the tasks. And we were able to actually outperform quite a bit of previous works in this particular angle on some of the meta world benchmarks as well as some of the in real world benchmarks. So diffusion model actually can be used as well. Okay, now finally kind of the topic of today, showing the potential, how the video models I actually showed earlier can be plugged in to some of the multimodal models for robot learning I showed you in order to solve actually as a zero-shot robot action policy. So how can this, for example, be plugged into something like this and then actually do zero-shot motion like this? And although this is kind of incomplete, I mean, we added it to archive version of our original kind of video understanding paper. But we can kind of say that it's showing actually a good potential. So just to recap, for example, in MBU, this was all about representing motion in the natural language, so that the later VLM, later LLM, higher level LLM can benefit from such motion information to decide what really is happening in the video. The architecture looked like this. It shows strong performance on video question answering. Now we are hacking this architecture and extending this to robotics, and it'll look like this. It looks almost the same if you actually look at it. It has the same frame sampling. It has something that you have not seen, which is actually the estimation of the depth in order to generate a 3D motion. But in terms of like objects and tracks, it's all identical. If I enlarge it, it looks like this. The only difference here is that here we are not only worrying about how the objects have been moving so far, but we also need to worry about how the object should be moving in the next frame, similar to the diffusion example I provided. But and also in the end, the LLM has to generate how the gripper should be moving instead of like answering to the question. Well, the question is how the gripper should move. So in some sense, this is about generating the answer. If you look at the actual kind of VLM, LLM, input to the LLM, this is how things were in video question answering. For the robot control is almost identical, except for the two things. One, we are actually providing the next position. We are learning to we are kind of prompting to kind of generate the next position of the gripper. And also we are kind of providing like the Z value, 3D value. But other than that, everything else is pretty identical, providing like the sequence of object coordinates, trajectories, and then asking the robot or asking the VLM to make the final decision that what should the action be. And it was able to do things like this. The red arrow we are showing here is like the motion or the object trajectory the VLM actually believes to happen in order for this this test to be successful, which is nothing but opening the door. And as you are able to see, we have a mechanism to map such 2D object information, 2D object motion into the 3D XYZ action. And by utilizing such 3D action, we were able to move the robot to do things. And once more emphasizing, it looks pretty similar to what I have shown you here. Why don't we use this one? However, this one is a diffusion model we trained quite a bit. This thing I am showing you here is completely zero shot. We didn't do anything. We simply took advantage of existing object detector tracker. We didn't even fine-tune VLM, LLM. We just gave it to an off-the-shelf VLM, LLM, and it was able to actually generate corresponding action. So zero shot video model actually became a robot model this way. Some more examples. I will not go into too much details. But if you actually look at the quantitative number, it actually did a pretty good job considering that this is a zero shot. Rank to more, our kind of diffusion model-based approach, compared to that, it was not really that far from behind, even without any training. Obviously, it had a limitation. It had no notion of what we mean by the gripper. The gripper was so small in the image, and we never really was able to capture the right gripper information based on the visual input. So it had no idea what to do with the gripper. So the success was pretty zero for the gripper. But as long as there is no gripper, it actually showed pretty good potential. Another kind of thing we tried was, I mentioned in the beginning that there is an approach called LBNet, which focused quite a bit on frame selection. We actually were able to try this LBNet frame selection approach with LLM to generate a robot action as well. In order to highlight the accuracy or the powerfulness of LBNet, we actually did, kind of augmented the data in this way. Clean kind of robot images are not really too interesting, so we kind of noised it quite a bit. Occasionally it gets like some good images, but mostly it's noisy, so it has to actually find out which frame is the good frame to take advantage of using LBNet and make the robot action decision. And as you are able to see, compared to just uniformly sampling the frames and then making the action decision, we were able to make much more reasonable decision by learning to select the frames serving as an input to the LLM mechanism. So that is pretty much everything I kind of wanted to talk about. So once more, I am emphasizing that computer vision models, particularly video models, have a great potential for their usage in robot learning. We had an opportunity to go through some examples of video models like MBU, LBNet, RangRepo. We also had an opportunity to go through some of the robot learning models, Lara, RangTumo using diffusion as examples of computer vision models benefiting robot learning. And then we also kind of were able to check the zero-shot capability, zero-shot transfer of video models into the robot action policy model, focusing on MBU and LBNet. That pretty much concludes my talk, but as mentioned by Mike, if you are interested in this line of research, if you like the flavor of the research I kind of talked about, please come to the conference in Seoul, Korea in September, and you'll be able to really enjoy the conference with all these research in a similar flavor. Okay, thank you very much.
Maybe just to kickstart, so for the zero shot example, that's quite impressive. And do you have any idea of that for the grippers? Like, is there any way we can deal with that? And right now it's 0%, but how can we add a 10%?
Yeah. So yeah, the lacking gripper definitely. I mean, we had no idea. I mean, the LLM essentially had no idea what the gripper should be moving, how the gripper should be moving, and what the gripper status actually was about. It originates from fact that we have been using a bit low resolution images. The gripper is pretty small. So it also may originate from the fact that we have been using a bit less powerful VLM. So maybe using more commercial VLMs like Gemini and with a high resolution image, maybe it can open up some potential. I mean, the easy way to do it is obviously to fine tune the VLM so that it can actually capture the fine grained gripper information, while not using the VLM's capability. So yeah, there is a potential, but maybe it's also that the VLM has to improve.
So I wonder, nowadays, some commercial models like ChatGPT can actually generate images or make annotations on images.
Generate images, okay.
Generation. So do you think this kind of capability could be used in this pipeline?
So this one was more about like text-based understanding. So it was not really directly used that way. But if we are talking about like generating images, maybe it can actually be used in a framework similar to this one. This one was about learning to generate like the motion kind of image. And if the GPT or like, Bell or any other kind of video generation is able to generate some dynamic motion videos like this, there is a good potential we can actually take advantage of it. I mean, some of the previous work actually, like AVDC, actually focused on video kind of generation, and then obtained motion information out of generated videos. So maybe it has more potential to be plugged into a framework that looks like this than the VLM or LLM based, like text based, like action reasoning.
Yes, so thank you for the talk. So your approach of using the motion arrows and images. So have you also thought about using contextual information? For example, if you are like a manufacturing setting, you have like detailed instruction manuals. So have you tried to use like prior information about that?
I think this is a great question. Our kind of attempt in generating action was pretty naive. But all these contextual informations are what people have been using for LLMs, VLMs, as in the form of the prompt or in the form of the context tokens. So adding such information and letting like VLM actually take advantage of it actually could have a great potential. We have not explored it because we really wanted to make it almost comparable to the video version of MBU, but I think that's a great potential.
All right, let's thank you.